And if the distance is much smaller than the wavelengths, this kind of medium can be considered as a kind of material or metamaterial. And then tailoring spectral properties of this metamaterial can be done by creating artificial elements in the form of very small, smaller than the wavelengths resonators, which has been demonstrated with split rings. And some years ago, we were studying superconducting version of that, which open path to lower loss and tunability in frequency. And it's very natural also to consider using superconducting qubits for this purpose. So the superconducting qubit is a nonlinear system. In particular, transmon qubit is a weakly nonlinear system, and it has an one can operate this nonlinear resonator in a two-level fashion by driving the transition between 0 and 1 levels. The transmon qubits have been used over the last almost 20 years, a bit less. I think 2007 was the first name invented in Yale group, 15 years. So, basically they are made of two Josephson junctions which form a squid, and then these two junctions are shunted by capacitor, and basically this capacitor is rather macroscopic. You see the size of this real structure is actually of the order of more than 100 microns. Then by applying magnetic flux to this squid, one can tune the energy level separation between the states of this qubit. And that's basically due to the change of the Josephson energy of the combined Josephson junction consisting of the two here. So as I already mentioned, these qubits have been, of course, used in many experiments and also being used for real applications now. When they're coupled to a resonator, one can use the resonator frequency shift or phase shift to read out the states of those qubits. And if one makes many of those qubits, then one forms the so-called Davis-Cummings Hamiltonian, where actually collective dynamics is also interesting to investigate. There have been a number of papers about that. So the subject of the talk today, I will tell you something about experiments where this kind of qubits are also coupled to the middle line where microwaves can propagate, but now it's not a resonator, but rather a transmission line. So it's actually an open space, one-dimensional space, where these two-level systems interact with propagating light. The Hamiltonian can be written in this form here, and this has been done by several, demonstrated by several theory papers. One can write the Hamiltonian for qubits, for propagating photons, and the interaction between them. And then the photons' degrees of freedom can be integrated out. And one is left with effective interaction between the qubits, which is characterized by the collective decay, which is the cosine of the argument, which contains the distance between the qubits. And there is also exchange interaction, which is a sign type. Actually, can also change the sign depending on the distance. And so far, experiments have been done with 2 and 3 qubits. And here we sort of thought about going to more extended system and see what actually happens. So the calculation of the organization of the Hamiltonian in one photon manifold deal gives the eigenmodes, eigenfrequencies. And there are, of course, modes which are characterized by superradiant behavior and modes which are characterized by subradiant behavior. And I will probably not discuss details because we'll come to this picture a little later. So the arrays of qubits seen as quantum metamaterials have been mainly proposed in theory so far, and the predictions of super and subradiance. One has also thought about band gap engineering. There is a systematic work ongoing in the group of Oscar Painter and Caltech. And one can also use this for a variety of other effects as generating non-classical light. One can entangle photons propagating in the transmission line by coupling them to qubits. So what is, of course, quite challenging is that those proposals which exist, multiple proposals which exist in literature, they require identical qubits. And it's very hard, of course, experimentally to make them identical. It's nearly impossible because all the handmade objects, macroscopic objects, they are slightly different from one another. But just give it a try was interesting for us. So first thing we tried was actually making a chip with 90 qubits coupled to transmission line. And then we just looked at the propagating microwave signals through the line. The qubits were separated by distance in units of wavelengths, which was quite small, smaller than wavelengths. And the lifetime of qubits was limited by the decay in the transmission line. So it's not limited by internal coherence. Now, the array was very long, as I said, and the distance was about 3 wavelengths. And without showing much detail, I'll just flash this picture here that as expected, we observed a band gap where the qubits collectively absorb light. And the saturation in this band gap was significantly higher power than some of the single qubit signals, which were away from the main band. So here were similar qubits and one was dissimilar. And therefore, the saturation was at significantly lower power. So this is the only signature of quantum behavior that actually you saturate transition 0-1 transition, and then the band gap ceases to exist. But of course, you cannot do much because the qubits are not identical, and this band gap, which appears here, is limited by disorder. So to do this more systematically, understand really details and comparing this with a real Hamiltonian, we went back and designed a system where we coupled only 8 qubits to transmission line, but now all those qubits were frequency tunable, so we can actually tune them to the same frequency one by one, and then see the results of interaction. And a single qubit coupled transmission line was first studied by Oleg Astafyev and co-authors in NEC lab in Japan, where they actually observed the major phenomena, which is the photon reflection from the qubit with opposite phase. So basically, there is a extinction in transmission of the light at the frequency of the qubit, but the photons are not absorbed; they are reflected back with opposite phase, and therefore the signal doesn't propagate. But of course, if you increase the power, then the transition gets saturated, and there are more photons. But of course, obviously, saturation power for many qubits should be higher than saturation power of 1 qubit. So this is an example of single qubit data, very similar to data of Astafyev. And we basically reach here extinction, which is over 99%. So the qubits are very, very strongly coupled. And nearly all the photons which come to the qubit at the transition frequency get reflected back. And you see the dip in the transmission here, and then corresponding change of the phase. And then one can fit and get all the parameters from the circle fit on the complex plane. Now, let us add more and more qubits and see what happens. Now we add the second qubit to the same frequency, and we see that the resonant line changes the profile. We get 3 qubits. We see the appearance of a sharp peak. And then if we add 4, this peak becomes sharper. And when we get all 8 qubits, then we see actually the emergence of another peak at the bottom here. So what we see, in fact, here, the whole band gap is a superradiant state of all the qubits, while the sharp peaks are signatures of the dark states. And this is confirmed by performing Lindblad simulations of the system, where we can actually get a very nice comparison with experimental data. You see this brown line nicely represents what we have measured in real data. Then it's good to characterize the collective decay, but for that, more convenient is to look at the reflection signal. So here you see the measurements in reflection, and then one can identify here this broad resonance, which is the superradiant mode, and then one of the dark modes, this subradiant mode, is appearing as a very sharp cusp there. So by measuring the widths of these subradiant modes, one can actually compare the predictions with theory, and there is interesting scaling of the darkest superradiant state line widths as a number of qubits in the power n to -3, which is also consistent with scaling of the predictions of those papers down there. It's not the main subject of my talk because time is limited. I think I will go over to more interesting slides now. So the collective decay is there, and the agreement with theory is quite convincing. Now we have 8 qubits, which are separated by a fraction of wavelengths. And then when we add more and more qubits, now the number of qubits is shown here on vertical axis, 1 to 8. Then we see the appearance of this band gap. Now the color is the transmission amplitude, and the dark color is basically no transmission. And then the crosses are the predictions of the eigenmode of the generalization of the Hamiltonian, and the limiting width of this band gap for infinitively long metamaterial with this fixed spacing between the qubits is about 6 times 3 widths of the decay limited single qubit line widths. But in our case, because of the finite lengths of the system, we observed widening only by factor roughly 2 compared to the single qubit resonance. This is the signature that actually the setup works, and we could also identify the good agreement with calculation when we, for example, fix 7 qubits at particular frequency and then tune the qubit number 8 through this collective resonance and observing the emergence and disappearance of particular lines, which actually has good agreement with theory. So the phenomena which I explained so far were expected in a single photon manifold. That means actually they could be explained for a fully classical model, which is harmonic oscillator. Now the quantumness of the system gets recognized by saturation, which you could see on this plot. For 1 qubit, it's about 100 minus 123, while for 8 qubits, it's well above minus 120. So this is the difference in saturation power, which actually tells that you need 8 times more photons to saturate 8 qubits compared to a single qubit. But it's not really well appreciated. Quantumness saturation is, of course, also something which is not exactly direct. More direct phenomenon would be demonstration of the phenomenon known in atomic physics, which is Otlet-Tons splitting. And in this case, you apply control tone, which drives the transition between the first excited and the second excited state. And this drive addresses the first excited state. So there is a splitting of the state. And then the splitting can be seen in the spectrum of the system. And similar phenomenon was observed by Astafyev's group over 10 years ago, but now we have 8 qubits rather than 1 qubit, and want to get the collective dynamics there. So what we then observe is the splitting. When we apply this control tone, the single peak splits in 2, and this is the signature which is known from Otlet-Tons phenomenon in atomic physics. Now, the calculation shows the collective dynamics, while in experiment we see that actually the line is split into few more lines. And currently we believe that these additional lines, which don't agree with the simulation, are due to the fact that by having 8 qubits, not all of them are identical. So if we tune the transition between 0 and 1 to the same frequency, it doesn't mean that the transition between 1 and 2 is the same, because they're physically different. And therefore, and we actually know the qubit which was a bit off resonance when we observe this splitting. So next thing we do, we try to use this very sharp feature in the middle of the transmission, which is a very narrow band with almost flat dispersion here, to demonstrate slowing of the electromagnetic waves, similarly to the phenomena which is studied in atomic physics and also in other systems. So basically, by applying different drive amplitude, we can widen the gap here. We can widen the gap from very small to wider and wider. And here, one would expect the slowest light, while if you move in this direction, increasing the control power, the velocity of propagating electromagnetic waves should basically increase. So the slope of the dispersion here is giving us the group velocity, and we see that this dashed line actually changes the slope, as I just explained by words. So then we have done real measurements here, and we have here on this plot several cuts. One cut is right there, the other cut is here, and basically the gap is opening at larger power. And then from the slope in the dispersion, this is basically the real data taken from amplitude and the phase. So this is the dashed line, which characterizes the inverse group velocity. And we see that we could extract basically from this dispersion indirectly the information about the decay of the light propagation through the system. And this is the agreement for 7 qubits. We took 7 because the 8 qubit was actually this line, which we didn't like in the autoton splitting. So, and the agreement between data and simulations is really good. I will skip some discussion of the theory, which can be found now in this paper here. Now, let me move over to a more experimental way of claiming that. In addition to doing the spectral analysis, we also measured the real delay of pulse propagation. So we were sending pulses with few photons through this line, and then by changing from one point to another, we were hoping to measure the real delay of the light propagation. And here you see that by changing the power, we see the change of the shape of the line. So this is the amplitude, and this is the time. The width of pulses is compressed here by a factor of 20 just to be able to compare them. So they're on the scale of a couple of tenths of nanoseconds and more. It's actually we used for this example, we use 50 nanosecond pulse widths. Now it's important also to say that we cannot go very deep into this cusp here because we need for the particular pulse widths, we need a particular width in dispersion. So there is a certain width of this pulse in the Fourier space, and therefore we could only start from the time which is roughly 1 over the pulse duration, from the frequency which is 1 over the pulse duration. So moving over to real data, these are the delays of the pulses measured in real setup by measuring the pulse propagation velocity. And these points actually also nicely agree with points which we measured indirectly from the spectrum. So the group indices, the group velocity is reduced by a factor of almost 1,500, and time-resolved experiments also demonstrate that. So I think my time is over. I go to conclusions. So all these beautiful measurements were done by a single person. This is Jan Brem, who recently graduated in my group. Brilliant guy, and actually did very systematic and focused work on this experiment. Basically, we have demonstrated the metamaterial with fully controllable 8 qubits. We observed the emergence of the polaritonic gap. We observed sub and superradiant states, and also scaling of the collective decay, and also measured the slowing light with group indices up to over 1,000. And if you want to learn more about these experiments, there have been those 2 papers. This is a paper coming out shortly in Applied Physics Letters. So thanks for your attention.
Thank you for a nice talk. And right now, questions.
Thank you very much for your nice and really impressive work. And could you comment in more detail about a possibility to use this waveguides with qubits for lasing? I saw one graph, but what are the perspectives? Or they are designed for something else? If not, then what could be perspectives of the structures as lasers? Thank you.
Well, for lasing, you need typically a particular structure of level, lambda system, which is not the case for these qubits, right? So they have this structure which is not exactly for that. And then you also need to have certain lifetime of particular states, which you need to pump the energy into the system before you start observing the lasing. I know that similar experiments are going on now in Astafiev's group, where they work with different qubits in order to implement the lasing. But lasing with these qubits, again, was actually an experiment. I would refer to the old work almost 20 years ago, where they've been able to see single atom lasing. And this is, I think, the paper published NEC group about 18 years ago, around that. So it's possible, but of course you need a particular level structure and also a particular combination of lifetime. In some cases you need to sort of tailor the decay to be able to observe the lasing, but this is possible. Yeah.
What do you consider as the main application of this structure?
I think the main application of this structure, there are 2. So one is creating non-classical light. That's basically producing entanglement between propagating photons and qubits. And the second is it can be also alternative architecture for quantum computing, where one could have coupling all-to-all. And there is a recent paper from Caltech where they advertise it and also show some data in a bit different setting where they make dispersion engineering using a chain of resonators. But basically, you have qubits, they will interact with one another if you are in the transmission gap, where in the band. But if you tune the qubits away in the band gap, then they don't interact with each other. So there is a possibility to explore this architecture and eventually implement some interesting quantum algorithms.
Thank you.
Another question.
Yes, thank you. I have a question. What is the role of dissipation? Is it some bound for the temperature of the system, or do you allow for dissipation?
Dissipation is there, of course, and dissipation shows, actually is reflected in the contrast of observation of the dark states. So we are limited by intrinsic dissipation, and therefore we cannot see all the dark states. Some of them have very long lifetime, but then the system doesn't live in this time because the system intrinsically decay. So, and dissipation is limited by the mechanism which we discussed today in the talk of Professor Siddiqui, where actually he has shown different mechanisms which contribute to the losses in superconducting qubits. And for these particular qubits, we were not really in the regime of hundreds of microseconds. I think the characteristic lifetime of the qubits alone was in the range of few microseconds. But it was limited by coupling to the line. And therefore, it wasn't critical for these experiments. It only prevented observing of some really deep dark states.
Thank you.
Actually, I have a question about this gap or some region on this picture, delta omega, and how it depends on interaction between qubits and resonator, or
There is no transmission line.
Transmission line, and is it possible to vary this?
Well, the coupling of qubits to the line is fixed. We cannot change the coupling constant. Therefore, the line width of individual qubit is just fixed by design. But of course, if you change the distance between the qubits, then of course the width of the band also changes. And if you have then very long chain, then I mean it's again not tunable because you basically need to redesign the whole array. Or maybe detune some qubits away, and then you will have on less qubits, but still fixed with the same fraction of the line widths. So I would guess there is not much in this kind of layout. There is not much freedom to tune these parameters.
Okay. Thank you. There is a question? If you have no questions, before we go to another talk, we give this small present.
Okay.
Okay. Return to second talk of this session and talk of Professor Thomas Ortler and from CIS Forschung Institute for Microsensing GmbH, Germany, and talk is titled Sensitivity of the Adiabatic Quantum Flux Parametron as Interface for Quantum Computing System. Please.
Thank you very much for your introduction. And now we switch from the qubit or from the pure quantum circuit to classical circuits, but they operate at the border to the quantum circuits. So our effort in this research is to build interface electronics with the potential to operate at very low temperatures. So maybe at the same stage or even on a monolithic chip together with the qubits. It's based on a collaboration between my company in Erfurt and Yokohama National University. So let's see, this is, okay. So just briefly, so CIS stands for Competence in Silicon, we develop sensors, and mostly silicon stands for semiconductor circuits, but we also do some superconducting circuits, and it's a private research organization. And I don't want to go into the details, but just showing that besides the superconducting quantum circuits, we also investigate diamond and NV centers in diamond. And recently we finished our first prototype of a magnetic field sensor, which can be used for industrial application. Actually, what you see in the center is a LED, and on top of the LED is a diamond with highly doped nitrogen, and around are photodiodes to detect the light, and this already is in use in a magnetic scale. Okay, in the superconducting field, we spent a lot of effort to developing packaging technologies. This is one example where you have a 5x5 millimeter chip and 4 flip chip connected cryotrons on top. And this is one of the assembly approaches we also use for the qubit integration. We collaborate with IPHT in Jena, also in Germany. It's very close to Erfurt. They are producing aluminum-based qubits, and then we connect them to the AQFP circuits, which I will tell you in more detail right now. So the motivation is very simple, and it's basically based on the energy dissipation in computing, but we don't plan to build a computing system with the AQFP. We plan to build interface circuits. And then I will speak a little bit about energy dissipation in general, and about the sensitivity, which is the main focus of this talk, because the question is, how sensitive can I make the comparator to get in contact with some very weak or very low energy component, and then I will conclude my talk. So I think I don't have to go in detail, but big data centers based on semiconductors, they have not only a big footprint, they also have a large demand for electrical power, and the idea of using more efficient computing systems is just to find some electronics which have a better energy efficiency. And maybe 20 years ago, the speed was most interesting for people. So clock frequencies were increasing, how many operations per second, and people were counting flops and gigaflops and so on. And today, most attractive or most interesting is this number, so the bit energy of 1 bit operation. And in this case, I have normalized it to the Josephson coupling energy because I'm interested in comparing different Josephson circuits. But in this second number, this is also very important. That's the energy delay product. It's not only important to have a low energy electronics, but also a certain speed is required. Maybe you don't need the fastest electronics, but the right product is important. So I put here one number up for CMOS. Of course, it makes no sense to give this normalization, but I have a typical gate, the QFP, the quantum flux parametron. At that time, it was driven in a non-adiabatic mode, but later people found a way to change the circuit parameters. You can drive it adiabatically. What does it mean? It means that your current phase relation has no hysteresis anymore. You use a strongly nonlinear current phase relation, but there's no jump. So the phase of the Josephson junction always follows the excitation current. And if you don't drive it too fast, then it can directly follow it. So the energy dissipation is very low. So to get the best number in this comparison, and you see how far you're also from the quantum limit. Okay, so now I switch first to the classical Josephson electronics, where you have the Josephson comparator as the most sensitive element to detect an incoming current. Basically, it's based on 2 Josephson junctions on top of each other, and you have an input signal, and the 2 junctions are part of a superconducting loop. So J1 is the driver, and it creates for every clock cycle, which is indicated here, for every clock cycle, it creates a single flux quantum, which is first stored in this loop, but the loop is too small, so the inductance is too small to store it. it creates a screening current which is larger than the critical current. So eventually it forces the stack of the two junctions to switch. But the question is which junction switches, J2 or J3, and this depends on the input current. So either J2 or J3 reproduces the clock pulse, and then if it was J3, you get also an output later. If J2 switches, you basically lose the clock pulse, and there's no information. And the practical circuit looks like this. You have here Josephson junctions. That's the clock driver, the pair in the comparator, and this is the output. You design it in a way that your threshold for the input current is around 0. This is not trivial. So if you make the two junctions equal, then you still have a large offset. You need to take into account that the lower junction has a load, and this is just engineering work. So electrical engineer optimize all the circuit parameter. This is just to give you an example, and it's the same circuit. And then later you investigate the sensitivity by scanning over different input currents. So the x-axis is the input current provided in this case from the bottom, and the y-axis is the probability of an output pulse. So in this example we applied 10,000 clock pulses and we counted the number of ones. If your input current is, for instance, minus 10 microamp, you get 0 output pulses. If it's plus 10, you get always an output pulse, so probability is 1. And then you have an error function in between. And you can see one important parameter here. This is the bias current of the two junctions, so IB1. And depending on the bias current, you see a different gray zone or different sensitivity. So this is one way to tune it, but the question is, so I put here 3 numbers, so is it getting, let's say, infinite better, or is there a limit? And we investigated this with such a circuit. This is the same comparator. It's surrounded by Josephson transmission lines to decouple it from the interface circuit, and we have a clock generator and output, and this is how experimental data looks like. Again, in this picture, you see a lot of different transition curves for different bias currents. In this case, I put the bias voltage, but that's the voltage which is turned into a bias current. And if you plot the gray zone versus this supply, then you see that you find a minimum point. So there is an optimal operation condition in terms of sensitivity. And for this circuit operating at liquid helium temperature, you reach something like 2.5 microamp. And this is giving you a lot of limitations for the best sensitivity you can obtain in ADCs or in other circuit elements. And it's also a limitation how you can connect to other elements. So we investigated, beside this current, other influence factors. One other factor is the clock frequency. And you can see it also depends on the clock frequency. So this is the real minimum. At very low frequencies, you can reach something like 2 microamp. But if your frequency goes up, then also this minimum point goes up. And if you reach something like 10 gigahertz, then already 5 microamp is a good number. So it's also a function of frequency. And last but not least, in digital circuits, one of the issues is timing jitter and delay. And you can simulate it, but you can also measure that the timing jitter and the delay of the comparator having a strong dependency on the input signal. And this is a problem, but it's very easy to understand. If your input current is far from the threshold, if it's really very low or very high, it's very easy for the comparator to make the decision. It's very quick, and it obtains the right result. But if your input current is around the threshold, so very close to 50%, it's much harder for the comparator to make the decision, and it takes longer. So you see an increase in the decision delay, but you also see an increase in the uncertainty. So it takes longer, but it's getting also more difficult. So this is also a problem in clocked systems, because you see here a big range. So it's like from 20 picosecond, it's going almost to 300 picosecond. And it's a little bit comparable if you're thinking about a two-dimensional hill and you're having a ball and you roll it to the hill. So if you go very left or very right, then it's very fast and it goes to the right decision. But if you almost hit the center, it takes the longest time. Eventually, if you go left or right. Same here in this circuit. So now I switched. This was the analysis of the Josephson comparators. Has been done many years ago. You can find all this. So all the key parameters are known. Recently, we started with our investigation of the adiabatic quantum flux parametron, and I will also analyze the sensitivity of this. So briefly, I want to explain the circuit. The AQFP consists of two Josephson junctions. They are in one superconducting loop, but in the center is a second inductor, and it separates the loop in two sides. I told you before that the current phase relation in this whole circuit does not allow a real switching. So it's always, let's say, following, the phase is always following the current. And you have an excitation line. This excitation line is driven by a sine wave, and you generate extra current in this loop. And in the transition point, the junction have to make a decision. You can understand this, that the current maybe goes clockwise, and it starts a current in J2 and in J1, opposite direction, but they both moving towards their critical current, and one of the junction is basically winning the race, and it changes and subpoint very quickly the phase, and then all the junction takes over this phase, and this creates a redistribution of the current to the center inductor, and then the loop is again in a stable operation point. You can also look at the potential energy. If there's no excitation current, then you have just one minimum point, and if you increase the excitation current, you generate two stable states. And for every clock cycle, the circuit makes a decision. So I just want to give some typical circuit parameters. In the experiments here, we analyzed AQFPs with critical currents of 50 microamp. This is the typical design value for circuits operating at 4 Kelvin. For our qubit control circuit, we aim lower critical currents, so 10 to 20 microamp, but they show already a little, let's say, bit error rate at 4 Kelvin. So it's a trade-off. But the other important question is about the sensitivity of this circuit. So I like to show you one experimental proof that the bit energy is really low. This is a nice experiment where the AQFP is connected to a network analyzer, and then you basically increase the excitation power, and you look how much of the power is taken from your system, and at some particular point you get a jump here. And if you calculate this backwards, then you get a proof that your switching energy is 10 zettajoule for 5 gigahertz excitation. And this is in very good agreement with the theory, and this is one of the things I like about the Josephson circuits, that the Josephson junction itself is easy to describe by mathematical equations. It's not like the transistors where we have very complex models with a lot of parameters you have to fit somehow, and they are not physical. So here it's in very good agreement, and we can also design quite complex circuits. One of the advantages is that the whole circuit always repeats the same fundamental cell. It's the AQFP cell I showed you before. You don't have to optimize and generate many, many different cells. It's basically an ensemble of many thousand of the same cells, and just the wiring depends what the circuit is doing. This is an example for a 16-word register file, which is part of a simple microprocessor we have designed and tested in Yokohama. I don't want to go into the details because I want to investigate the fundamental cell. This is again showing you the circuit diagram and the layout. What you see is that the actual squid with the two junctions is very small. This is the excitation line, J1, J2, and this is already the loop. And the physical large part is the transformer, because you need an output transformer at the output. This is one of the reasons the scaling is limited for the circuit. You have a cell size of about 30 by 30 micrometer due to this transformer here. This is how typical, let's say, signals look like. That's simulation, because I show also phase signals, and this is an excitation current. The typical excitation is about 1 to 2 milliamp, and you have currents in the two junction in the range below 100 microamp, because you have 2 times 50 microamp junctions. And depending on the input signal, you can see where it switches. It's switched either in the one direction or in the opposite direction. The simulation also includes noise, but you see here, obviously, the sensitivity is good enough to overcome the noise. And these are the two phase values of the two junctions. So from the phase, it's very easy to distinguish which junction switches. But you also see here, this is all a transient change. There's no jump in the system. To measure the sensitivity, you do the same thing. You operate this with maybe 10,000 clock cycles. You change the input current and you sweep. And this is again such a measurement as I have shown you before. The input current on the x-axis and the probability of switching on the y-axis. And then you can fit the data. What was very interesting for us to see that it's in very good agreement with the error function. And why I was particularly looking at this, if you carefully look at the circuit here, you will find the Josephson junction have no external resistors, so they have no damping resistor. It's not necessary for the AQFP because your junction never switches, so it just follows, and the loop is so small that it's a very strong damping due to the inductor actually. So it has no free running of the phase. And then the question is, what is the origin of this gray zone or of the noise? And you want to make sure it's pure Gaussian noise and not something else. That's why I plotted here the difference from the error junction fit, which is also very small. So this is 0.4%. And this is just because of the statistics. If I put more numbers, it even gets better. So it's in very good agreement, but most important is now the number, what is the gray zone, and then we investigated this for different excitation signals. So the red curve is the gray zone, and most important dependence is on the rising edge of the excitation current. So if your excitation is very high frequency, then unfortunately also your gray zone gets large and you have this dependency. So for instance, for 1 megahertz excitation, you have something like 0.45 microamp. And at some point here it saturates at the lowest value, it's just below 0.4 microamp. For 4 Kelvin, that's the lowest value we could measure. And for all frequencies which are faster than here, it increases even. And you can also see a small threshold shift. This is the threshold here. It should be 0. Due to some imbalance, it wasn't 0, but it's also increasing a little bit. So the dependency on the excitation is normal. You can easily understand it from the bandwidth of the noise you allow. Because if you are operating at very high frequencies, you have a much higher bandwidth of noise coming into it. And the difficulty is to explain this saturation here, but we are currently investigating different temperatures to understand what is the influence of temperature to this. And this is an extension of the previous data by simulation, and we went to much higher frequencies and want to see what happens then. So at, for instance, 1 gigahertz, we are already at about 2 microamp gray zone. So this is very similar to the RSFQ circuits. So it's not really giving me significant better performance than the SFQ circuits. But if I go to something like a megahertz, then I can have at least a factor of 5 better sensitivity in comparison to the SFQ circuits. And lower frequencies is actually attractive because the AQFP power dissipation is a function of frequency. So if I operate it slower, I also get less and less dissipations. And of course, we investigated also all other parameters. Most important parameter I showed you before. But for instance, the excitation amplitude has no influence. That's very interesting. So the excitation slope has a strong influence, but for the amplitude, threshold, and sensitivity are independent. This is very good and is very different to the Josephson comparator. And now you can do some estimations. What is the maximum input signal you need? And here are some data points. And this is the input current you apply. And we assume an 0.4 microamp sensitivity. And then with this input currents, you get a certain probability for switching errors. If you want to build a very stable digital circuit, you're aiming for something like 10 to the minus 15. So then you see here you need input currents of about 5 microamp. And this is one of the reasons we're using AQFPs with lowest critical current of 10 microamp for our control circuits, because we want finally to come into a very classical stable regime. Maybe there are a lot of other influence factors. It will be hard to prove that we are here, but at least from the, let's say, first principles, we don't want to violate this. And I want also to give you a brief explanation why the Josephson comparator is about a factor of 5 worse than the AQFP comparator. This picture shows you a simulation of the Josephson phase for the 2 junctions of the comparator. And this is all around 0. So if I take the 2 junctions and allow them with some thermal noise to fluctuate, I get a distribution. And you can also describe this distribution. And there's a paper from 2012 which gives the explanation how to describe it. But you can also see that there is a certain shape which supports this direction. So if phase of junction 1 increases, phase of junction 2 likes to increase in the same way. This is due to the loop configuration in the Josephson comparator. In the AQFP, it's very different because your loop is much, much smaller, and you have another mode that one junction is driven in a positive way, the other junction is driven in a negative way. And you see here that it's not possible or not very likely that one junction increases the phase and the other one does the same. And this is actually the direction of the input current. And this is more clear in this picture here, that this is again the 2 structures, and I have a certain distribution coming from the thermal noise. And then the question is, what is the influence or the impact of a clock pulse, and what is the impact of the signal? And it's very important to see that the signal here belongs to the very narrow distribution. So this makes the AQFP comparator more sensitive than the Josephson comparator at the same temperature. And I don't want to give you some formulas, but you can also calculate this. But first we want to get more experimental data to compare this theoretical approach to the measured data. And this is some example for what you can do at low temperatures. So our circuits now are tested at 4 Kelvin with 50 microamp junctions. If you assume a very complex circuit with 100,000 gates at 5 gigahertz, you get a total power dissipation of 5 microwatt. This is still extremely low, but it's also a very complex circuit. So let's assume we want to go down to 300 millikelvin, and we are using much smaller critical currents, in principle 4 microamp as possible, and still a complex circuit with 10,000. Then we lower the frequency to 100 megahertz. Dissipation is a function of linear function of frequency. We end up with something like 0.5 nanowatt. And this is still possible at this temperature. So we think we have a good potential to come close to qubit circuits. And right now we're doing this flip chip bonding with qubits from IPHD, but we don't connect them at the moment. We just keep both parts independent and want to see that we can run both at the same time. And the next step will be, of course, an electrical or magnetic coupling of both to use this as interface electronics. So I'm at the end of my presentation. I'd like to summarize that we have measured the minimum gray zone of the AQFP circuit at liquid helium temperature to be around 0.4 microamp. And the good thing is it's not influenced by excitation bias. And also, I haven't shown you the experimental data, but also some flux bias is not changing the sensitivity or the threshold. This is good because we may have some flux bias near to the qubits, so therefore we want to know this. The experimental data is in very good agreement to all the theoretical formulas, and we have investigated the dependency on the slope and have a good understanding of the mechanism, so we can also optimize the circuit. Everything operates extremely robust with 50 microamp junction, and with 20 microamp junction I can tell you that we can also get good results at 4 Kelvin, but we have, from the theory, one switching error in around maybe 10 to the 9 clock cycles. Experimentally, we have not investigated so much data, so we haven't seen it in experiments. So the 20 microamp circuits work stable, and we did this extrapolation. So I'm at the end of my presentation. Thank you very much.
Thank you for a nice presentation, and right now time for questions.
Thank you, Thomas. Can you go 2 slides back? There was a table, yeah, here. Is this 100 megahertz a limit for low temperatures, or it's a by design?
No, it's not a limit. It's a particular design for our
Okay.
setup. But in principle, you may even consider lower frequencies. It depends what you want to do.
Okay.
If you, for instance, want to upload flux bias parameters for a lot of circuits, then you may do it just once, even with a megahertz or so, and then it's silent. Okay. But of course, if you want to have a continuous readout, then you have a certain repetition rate here. But you can also put here 5 gigahertz, then you get a higher dissipation. Yeah. So it's a trade-off.
Okay. And for the 4 Kelvin, 5 gigahertz is about the limit.
Yes.
What is the fundamental reason for this?
It's very simple, because it depends on your critical current density, and you have a maximum digital speed, comes from the plasma frequency, and you need to be about a factor of 10 below. It's a rough estimation. So this is based on the 10 kiloamp per square centimeter process from ACE in Japan. And this allows you an adiabatic operation of 5 gigahertz. If you would have a higher JC, you could go a little bit higher, but it's still in this range.
Okay. Thank you.
Actually, we don't aim for frequencies like this because we don't want to come close to qubit frequencies.
Mm-hmm. Okay.
Other questions?
I was going to ask you about Mach-Camber parameters for your junctions in the balance comparator and in AQ comparator.
So in early designs, we used the Mach-Camber parameter of 1. But later, we completely removed the resistors. So they have a Mach-Camber parameter of maybe 20, 50, we don't know exactly. The junction itself is not externally damped. But the loop configuration here provides a very strong, you can see it as a damping. The phase cannot make jumps.
But using off-tunnel junctions with high Mach-Camber parameter sometimes.
That's true, you can extract it, but we don't even have junctions to measure it on the chip. I can check data from Japan, what they have, but in all the circuit, they are always in these loop configurations. So they are basically shorted by an inductor. So this loop is about 2 pico.
Another question?
I'm wondering, what is the readout time, your target readout time, and what is the ring down time, which would, of course, limit the repetition cycle?
So this goes into the direction why we choose the 100 megahertz. So we think we have ring downtime of about a nanosecond. And we want to make sure, so we choose 10 times this number to make sure everything is really in equilibrium when we start. And the readout is just depending on this slope, because you have a certain fraction of the slope where the comparator is sensitive. So if you think about 100 megahertz, then this is also, again, roughly a nanosecond is the readout time.
Okay. Another questions? Okay, I have a question. Are there some works for not a single adiabatic comparator, but a network of comparators? If this is there, what is about interaction between basic elements? Or it's just independent elements?
It's a good question. I don't know about, let's say, scientific investigation of this, but one of the features in the complex circuit is that you have a lot of AQFPs connected to one excitation line, and they're all making a decision at the same moment. And we observe that if they're all in a digital mode, it means they get all a very well-defined positive or negative input. Then there's no problem. But if you drive more than one with an excitation line in this, let's say, analog mode, where you have a very sensitive input signal around 0, then you see a crosstalk between the comparators by the excitation line. So you have to take this into account. You can clock complex circuits with one excitation line, but if you have more than one comparator, you cannot easily connect this.
Thank you. Okay, if
Can you comment on the closed cycle refrigerator operating for AQFP circuits compared to SFQ? Is it same difficulty, or it's more sensitive to closed cycle refrigerator noise, or?
It's very robust,
Robust?
To the clock. I mean, you have an AC clock, so you feed a sine wave to the cryostat. So you need at least one, maybe 2 excitation lines at 100 megahertz or something like this. But you don't have a propagation of jitter, so every time it's synchronized by this external clock, and the amplitude of the clock is not increasing by the circuit complexity, so it's fixed.
Okay.
I think that's all, and thank again for this presentation, and this is diploma.
Okay, thank you.
Okay, and we go to another last talk of this first part of. Yeah. Speaker is not here. Ah, okay. Okay. No online presentation also. We will start for circuit. No, we will start second part of the session for circuit. 16th. Okay. introduction, and it's a great pleasure to be here. And my talk is about frustrated superconducting quantum networks. And main idea of the talk to give introduction in very excited topic, frustrated solid-state systems, and how superconducting quantum network, qubit networks, can bring a new attention to frustrated solid-state systems. And work has been done at Ruhr University Bochum, Germany, and just a minute. And outline of my talk composes of 3 parts. First, motivation for study, superconducting quantum networks, frustrated quantum networks. And second part, what is frustrated superconducting quantum networks, and especially what kind of interaction between basic elements we can introduce in superconducting quantum networks. And first for electromagnetic interaction, and second, interesting story which appears for some particular network lattices, for example, Kagame lattices, and it's called topological constraints, which provide some non-trivial interaction between different elements, different qubits. And finally, results, what kind of novel quantum phases, macroscopic quantum phases, and quantum phase transitions we can establish in frustrated superconducting quantum networks. Okay, first, as we hear today from nice talk of Professor Bazovich, we know about many systems we can call strongly correlated frustrated systems. And solid-state systems which provide, for example, transport properties which is not described standard textbook with a free fermions, free electrons. And idea is we have to include into account interaction between electrons. This term, for example, very famous Hubbard model. But then idea is to trace out fermions here and establish some Hamiltonian which works as a interacting spins on some non-trivial lattices. And moreover, these coefficients, exchange integrals, can be different signs and provide very interesting specific properties. And for example, 2 systems, one organic metallic material and another is novel superconducting systems which provide some Kagame lattice here and also some non-trivial exchange integrals here. Okay. Then another interesting system, magnetic macromolecules, which can be linear system or circular system. And again, the same story. We have for one bonds, we have exchange integral is positive and another is negative. But in any way, this is just some Hamiltonian, spin Hamiltonian with different parameters which can be different signs. Okay, and then result for this so-called frustrated, natural frustrated systems, non-trivial ground state. For example, if we have all parameters the same, we have ferromagnet interaction or antiferromagnet interaction and all spins in the same direction. But if we have different signs of this interaction, we produce some non-trivial ground state. Okay. And then we turn to superconducting arrays of Josephson junctions. Long time ago, people tried to see what happens in diamond chain of Josephson junctions. And if you have no external magnetic field, in this case, all faces of these islands or Josephson junctions is 0. But in the presence of single flux quantum, we have two different states in a single plaquette, anti-clockwise and clockwise. And then question is, what happens in system if basic element can provide two states, and then we have interaction between basic elements. Okay, and mostly this is Hamiltonian, and long time ago people realized there is very interesting phase for some range of parameters where we have single plaquette composed two states plus interaction, and we have so-called nematic Latergen liquid state. And then question about how it's possible to obtain this or some properties what we need for this system to observe this. Okay, and then for modern superconducting quantum networks, different types of Josephson junction, interacting Josephson junction systems. For example, 3 Josephson junction in basic elements, and then we have more complicated 5 Josephson junction in basic elements. And then question is how to provide interaction between these basic elements of superconducting quantum networks. One idea was, we can see from previous talk of Professor Ustinov, and for example, we have some resonator or transmission line, which due to excitation and absorption of photons provides long-range interaction between different elements of this superconducting network. Or it's possible, for example, to make many different networks composed of many Josephson junctions, and to see very famous Ising model in transverse field, and to see what is the ground state if we produce parameters of different signs here. Okay. And finally, for this motivation, and question is observation of non-trivial quantum phases called spin liquids. And for example, we see for Kagame lattice, for some range of parameters, we have, for example, this one state and another state in different direction, clockwise, anti-clockwise, and what is the combination of this in large system. And similar story for set of Josephson junctions here. If we have, for example, one bond has a negative sign, positive sign, and then we have very non-trivial distribution of spins here. And another story is due to Phil Anderson many years ago. If we have, for example, triangle, we can produce quantum state, entangled quantum states of 2 spins for one bond and no in other bonds we have just product of states. And then we have spin liquid of these strongly entangled elements. Okay, and how we can make, for example, in a superconducting network, for example, this is a dynamic system. We have a set of qubits and apply some pulses and interacting qubits, and we see, for example, this area we have for some particular time to provide strongly entangled states between, this is for 3 qubits, and in this area we can provide strong entangled of 3 qubits. Okay, with this motivation then I put 2 exemplars of Josephson arrays, Josephson network with pi junctions. Why pi junction? Because pi junction provides negative interaction in some bond. And then I consider sawtooth chain. With a model, we have Josephson junction, 0 type of Josephson junction. It means critical current is a positive here. And on these bonds, we have Josephson energy alpha EJ, and alpha can be negative. Alpha changes between -1 and 1. Then we can introduce frustration parameter, which is 1 minus alpha divided by 2. Okay, and then consider quantum dynamics of this system. We have potential energy for this network and kinetic energy. And then question is, what is the macroscopic quantum phases we can obtain here? First of all, we consider classical regime, when kinetic energy plays no role. We have potential energy, and then we see what happens. If frustration is less than this critical value, we have ordered ferromagnetic state. All phases on islands and also Josephson phases are 0 in ground state. And shows here. But if we go in this region, we have disordered state. It means single basic element can be with some vortex inside, which can be clockwise or anti-clockwise. Okay, and moreover, phases on islands has some particular value which depends on frustration. Then, for classical case, we have just some combination of different vorticity in basic elements. For example, anti-clockwise, anti-clockwise, clockwise, and so on. Okay, and then question is, what happens if we include quantum fluctuations? In this case, we have to provide a phase diagram for quantum case. And one parameter is just ratio of capacitance energy and Josephson energy. And here frustration. First of all, non-frustration regime, where we have just ground state, ferromagnet ground state, and we have standard Berezinski-Kosterlitz-Staulis quantum transition in this case. But important is we have including kinetic energy only energy of Josephson junctions, not capacitance to the ground. Okay, and what happens in frustration regime? Each triangle has 2 states. We have double well potential, and we have just a tunneling, amplitude of tunneling between two states in each basic element. But without capacitance to the ground, we have no interaction. It means we still have all basic elements is just independent of each other, and we have product of states, which is for basic element we have superposition of two states, and for global system we have product of these states. Something exciting. But then we have to include into account, to provide interaction, capacitance to the ground. Capacitance to the ground. In a non-frustration regime, we have still ferromagnet state and just different boundary, but also nothing spectacular. We have Berezinski-Kosterlitz-Staulis quantum transition here, and that's all. But what happens in frustration regime? This is completely different story because we have interaction. And due to this interaction, moreover, this is long-range interaction due to capacitance to the ground. And this is change sign if we go to two-dimension case. One is a coordinate and another is imaginary time. In this case, we obtain new phase, novel quantum phase, and we see what happens. In this regime, we have just a random number of vortices in one case, in one basic element or another element. And this is just so-called disordered state, and in fact, it's the product of superposition of states as before. But for small parameter G, we have interesting story. We have in coordinate, we have ferromagnet interaction, and we have ordered in one direction, but in time, imaginary time, we have antiferromagnet case. It's called stripes quantum phase, and this is some special entangled state. And also we have close to this part, we can find some defects in this state. Okay, and then another example, we go to frustrated 2D Kagame structure. Again, idea is to introduce in some lines, we have pi junctions, and to see what happens. Again, in the classical case, we have just potential energy, and basic element, single triangle, provides two states in frustrated regimes. Again, clockwise and anti-clockwise. Okay, but even here, without quantum fluctuations, situation like this, if each triangle can be clockwise or anti-clockwise vortex inside, we have 2 power n states. But we have this, when we go around this plaquette, we have especially constraint. The total phase here can be 0. Immediately, instead of 2 power n states, we have 2 power square root of n states. For single plaquette, instead of 64 states, we have just 14 states. 14 possible states. And also we have interesting in classical regime, interesting results, in some direction in x direction we have a strongly correlated system. In y direction we have strongly correlated pattern. In x direction we have no correlation. Okay, then we have to include into account quantum fluctuations, taking into account this strange interaction due to topological constraint, total phase equal 0. And we see what happens. We have 14 states, low-lying 14 states. If, for example, amplitude of tunneling between red and green vortex is 0, it's exactly here, we have 14 degenerated states. And then we include tunneling between red and green vortexes in this plaquette, and we see some lifting degeneration. And to see what happens if, for example, we have 3 states which is very close energy, then another states with a larger energy, and so on. This is influence of quantum fluctuations and influence of these topological constraints. We have no another type of interaction except topological constraints. Okay, in summary of my talk, and we can introduce and some frustrated Josephson junction arrays, network of Josephson junctions, quantum Josephson junctions, and frustration is introduced, first of all, with a combination of 0 and pi interacting Josephson junctions, and different system can provide long-range interactions. For example, capacitance to the ground, coupling to a low dissipative resonator or transmission line. And second part is a 2D coherent frustrated superconducting quantum networks, Kagame lattice of small junctions, and long-range interactions due to topological constraints. Some phases must be, total phases must be 0 if you go around some loop. And for large system, we have many constraints. For single plaquette, we have one constraint, and for large system, many topological constraints which have to be included into account. Okay, and goal is the following: to see different quantum phases and quantum phase transitions which can appear in this superconducting quantum networks, and then try to establish specific Hamiltonian and to see the very interesting quantum phases, for example, spin liquid and quantum spin liquid also. Thank you for attention.
Thank you, Misha, for your talk and also for leaving a few minutes for questions. Please, Sergey.
Does it mean that you found analytic solution for the frustrated spin liquid?
Okay. I can say for this system which we consider, obviously we can heavily based on some numerical analysis or some approximation like mean field theory. For example, for quasi 1D system, because it's long-range interaction. Moreover, this is with different sign. You can just to use mean field approximation for this. And this is first part. Second part, connected with 2D Kagame lattice, you have to include, due to very small number, total number of states, not 2 power n, 2 power square root of n, you can go to, again, for numerical analysis for larger system, much larger systems than standard case.
Okay, thank you.
More questions? I'm wondering for this dynamical coupling in the first case. So you have this capacitance to ground, which is needed for coupling. Is capacitance of the order of the junction capacitance?
No. This is, we can see the case when this is C0 much smaller than standard case, much smaller than capacitance of the junction.
Okay, so this
It's not necessary to be just that.
it has to do with the
It's a standard.
with the split level separation and not with the net energy of the junction.
No.
Understand? Okay. And
This
then
is just provide some small interaction, but important is this is not nearest neighbors interaction. It's long range like you have a photon in a resonator. But just one important point. This is power dependence, not just the same interaction between for large system. Is decay, but some power decay is 1 divided by r squared.
But pi junctions you don't necessarily need. You just consider a general case of alpha varying from negative to positive. So if one does this experiment simply with conventional junctions, would one see these phase transitions as well? I think so.
Okay, point is, and you have to create in single element double well potential. There is a mapping if you just work with magnetic field for flux quantum and all junction are positive standard flux qubit. The same story.
But then you have coupling between flux qubits, right?
Yes, but then we have a coupling between flux qubit. But point is, in this model, you have just one point in magnetic field. You have in magnetic field, if you change magnetic field from this point, immediately you have double well potential, not the same amplitude.
Okay, you need to have the resonance frequency of the. The double
For
well
this
potential
model is very important. For this model, be the same type of potential. So double well potential without splitting between potential wells. Minimum of potential wells.
You mean it should be symmetric double well potential?
Yes.
Okay, but then you have some split levels.
Yes.
And then you want to adjust the frequency of the split levels to another frequency which is dictated by capacitance. What is this frequency?
Not necessary. You have just model where you have this no resonance. No resonance.
So capacitance is just needed to have the coupling.
Produce interaction, and then question is what is the quantum states? Because in classical state you have just red, green, for example. And but in quantum case you have superposition of states in single element, and then question is how you entangled in a huge system this state.
Many body problem.
Yeah.
Okay,
this
thanks.
Exactly.
Any further questions? Okay, let's thank the speaker again.
Yes. Yeah. Yeah. Thank you. Okay. Okay.
The next
Okay.
speaker of the session is Iman Askerzadeh. And he's going to speak about influence of enharmonic and frustration effects on Josephson qubits characteristics.
Yes.
Don't press this one. Only this is pointer, and then this don't touch.
I know. Thank you. Thank you. I would like present my result about influence of enharmonic and frustration effects in Josephson qubits. Gelmedi. Bir saniye. Bak şöyle. Just one say. Here problem related. Başka, you can also, can try, but problem related with just one. Ne oldu? Şimdi bir defalık etti. İlk tuş bastım yani. İlk ne oldu? Evet. Bu var, başka da yok. O orada kapanacak, bende değil. Yes. The same problem ya, şeyde hiç değişmedi. Ancak şeyi gösterir. Please try your.
Maybe they can change slides for you.
Yeah. Yok değişmedi ya, o şey olmuyor. Oluyor da sen buradan page up, page down ölebiliyorsun ya, burada şey. Tamam. Bak şimdi oldu. Ya tamam. Evet. Tamam olabilir şimdi. Aha. Yok değişme. Evet tamam. Tamam şimdi oldu. I am sorry. Here first part overlapped with my presentation for summer school in the first 2 days, and here I present this tunnel structure Johnson Junction, and a lot of version of, for example, superconductor constriction and superconductor type of Johnson Junction, SNS junction, and superconductor ferromagnetic superconductor Johnson Junction. And this one, here also I present new result related with observation of Johnson effect in Bose-Einstein condensation in cesium atoms. This one, Fizerev letter, 2005 years. And here also for young peoples I present fundamental relation in Johnson junctions. This one, stationary Johnson junction and non-stationary Johnson junction, and here Shapiro-Stapes case, and also general equation for the study of dynamics of Johnson junctions. And our aim here to take into account other parameters, symmetry and multi-component character of Johnson of superconducting state on supercurrent relation, on Johnson current relation. Here also for young people are present structure of superconductor of the parameter in PCAs, in compressed superconductors. In compressed superconductors we have, as you know, D-wave character of other parameters, and in the 2002 years was discovered two-band electron phonon based MgB2 superconductors, and in 2008 years it was discovered ferron based superconductors, and these superconductors seems, these two class seems many band superconductors. This one MgB2 is 2-band superconductor, and this one, in the case of different compounds, or ferron-based compounds, there are sometimes possible 3-band, or sometimes possible 4-band calculations in study of superconducting state in these compounds. And here, in study of properties of Josephson junction in such systems, for example, in the case of single band, 2-band case, and in the case of single band, 3-band Josephson junctions, in this case, we should take into account two-channel character of Josephson current because of, as you can see here, this one difference of phase in Josephson junction, and here we have phi. This phi related by the epsilon parameter. This one epsilon parameter, it means free energy functional, Ginzburg-Landau functional interband interaction parameter. If epsilon is positive, then we have opposite character of this two-channel current, and in the case if epsilon negative, in this case we have in the same direction Josephson current, and here total critical current is the sum of two critical currents. In the case of 3-band superconductors, here also in the case of 3 identical Josephson coupling between other parameters, here we have 2 pi over 3 and 2 pi over minus 2 over 2 pi over 3 phase difference, and also in this case we have 3 Josephson current, and here in our study we will use general expression for the calculation of effective critical current in such systems. And here I also present equation related with calculation of critical current in the case of D-wave superconductors, and here result of Sigrist rise. As you can see here, final result is determined by the angles theta le and theta re. This one D-wave here taking into account D-wave character of other parameters, and as you can see here, theta L is the angle between phase plane of junction and D-wave parameter, and similar calculation also was conducted by Tanaka using green function methods, and in general case we have sine phi and cosine phi terms in supercurrent, and here also calculation is the case 2-band superconductors here in Amelianchuk, and also shown changing of current phase relation in the case of 2-band superconductors. And here experimental results by Bauch, and here experimental results related with ratio of second sines to phi term to amplitude of first, this one sinus phi. And as you can see, at low temperatures, it was evidence of increasing of amplitude of second term. It means that in study of characteristic of qubits based on Josephson junctions with unconventional with unharmonic current phase relation, we should take into account such effects. And here I also present some calculations, standard calculations in the case of Josephson dynamics, taking into account this one is equivalent scheme of Josephson junction, and here shunt resistor and shunt inductor. And here I present some results related with calculation of effective critical current, inclusion of second harmonic, this one sinus sphere, and inclusion of fractional also term into current phase relation leads to changing of effective critical current, and here there are calculation of maximum of such function as function of alpha leads similar results, and as you can see at low alpha we have quadratic behavior, and at high alpha we have linear behavior, but in the case of fractional term we have approximately linear behavior. And here also some fundamental moments related with superconductor qubits, and here about Shor algorithm, which is the beginning of quantum computing. Last year's this one, as shown by Shor, in the using quantum Fourier methods shows that exponential problems can be converted to normal polynomial problems, and development of technology leads to realization of qubits and quantum calculations. And here also simple, maybe for young people, for pedagogical. Yeah, you're right. I use, yes, yeah. This one here, this one my fault. You are right, Brian. Here classical systems and here quantum systems, and changing of state of one of qubits leads to changing of over to quantum systems, and this leads to quantum parallelism, and as a result to the results related with quantum computation. Quantum computation and entangled state, this one, it is possible the state of in quantum mechanics, if take two qubits, in this case we have no entangled state, we have such equation alpha delta and beta gamma is 0. It means that in this case we have factorization, and wave function can be presented like production of two wave function. And if no factorization, it means that entangled state, and entangled state was discovered many years ago by Schrödinger, but only last years people, researchers would like to apply in also this yours. This one here, as you can see, also two qubit state and Bell state, and here also Einstein-Podolsky state. This state is states with maximum entanglement state. And here I present also a schematic of quantum computing in the case. As you can see, quantum computing is this one quantum mechanical system embedded to classical environment, and here we use algorithms, this one unitary transformations of wave functions of qubits, and the result can be measured, and as a result we can found the solution of the problem. And here also I present possible qubits, and there are microscopic and macroscopic. In our case we study this one charge energy and Josephson energy, and ratio of these two energy is the important parameter in study of dynamics, because of in the case if we have Coulomb energy is higher than Josephson energy, here we have charge behavior, and inside small Josephson junctions, it is possible column blockade and related phenomena, and using here Josephson junction and gate and here Eastland, we can tuning voltage on Josephson junction, and changing of number of Cooper pairs leads to results similar to and in opposite case, when we have two limits, and in these limits Josephson energy is higher than here we have a phase as sensitive parameter, and as a result we and also here as you can see here, changing of this ratio, and this ratio is proportional, we can calculate this one is proportional to A in square. It is A is the junction area. In the junction area, and here last year's pupils in different laboratories realized different types of Josephson qubits, superconducting qubits. And here I present my main aim of our study is the calculation of plasma frequency in anharmonic Josephson junction. Anharmonic, it means in current phase relation we have, because here we have classical harmonic oscillator spectrum, and here as you can see omega plasma is plasma frequency also can be calculated using of our effective critical currents. Effective critical currents. Well, yeah. The same problem, yeah? Allah. Yeah, no problem. This one. Yine çalışmalı. Ne oldu? Ne oldu? This, yes. And in the case of current phase relation in which we have a second term, anharmonic term, I show changing of plasma frequency. As you know, plasma frequency is proportional, is square of effective critical current, and effective critical current calculated in the case of sines phi and alpha sines 2 phi. And in the case of single band, two band superconductors, many band superconductors, then here we have a changing also this one plasma frequency. In the case of pi Josephson junction, it means that in this case we have synfase supercurrents, and in this case we opposite direction Josephson current. And in similar way, I would like to show changing of plasma frequency in the case of three-band superconductors, and here IC3 over IC1, and here a changing of character of, as you can see here, we have this one, first one, this one, second one, and in this case we have result which is similar to two-band case. And in similar way, this one, the study of phase qubits. In phase qubits, we use only single Josephson junction, but in the case of flux qubits, we have superconductor ring with Josephson junction. If we take Josephson junction with anharmonic current phase relation and maybe a single band, multi-band superconductor, in this case, changing also characteristics should be taken into account. And here also general expression for potential energy. And here I show plasma frequency in flux qubit with anharmonic character of Josephson junction. As you can see here, we have a picture similar to if L is 100, in this case we have this one quadratic behavior, and here we linear behavior, and this one similar behavior of single Josephson junction and changing of inductance of AC squared. In this case, presented in this picture, and changing of this one, changing of plasma frequency will lead to changing energy difference between states 0 and 1. And also here I present results related in the case of also single band, two band superconductors. As you can see in this case, we have a single junction behavior, as you can see, and changing of character of plasma frequency in the different inductance parameter also present in this picture, and here also present the result of flux qubit in the case of single band, three band superconductors, and changing also plasma frequency in different cases. As you can see here, we have behavior related with the case in the case of single Josephson junction, but in the case of low inductance AC squared, we have behavior also similar to this one, but there are total increasing of frequency, and here also we have similar pictures. And here also I would like to say any words related with silent qubits due to exclude external fluctuation related with applying of the external magnetic flux. In the case of second harmonic in current phase relation, it is possible take such, for example, potential of Josephson junction, and in this case we have as shown in this study, we can creating of silent qubits. Silent qubit, it means without any external magnetic field, and in this case, due to absence of external magnetic field, coherence time should be better. And here also similar calculation was conducted in our study, maybe many years ago. And here, as you can see, Mathieu pictures, and in these pictures we take into account inclusion of second term leads to changing of energy spectrum of total system, and here result of our calculations. But this one generally our calculations, but last year calculations I show few minutes ago. Here changing of delta 0, delta 1, this one first band and second band using Mathieu equations with anharmonic current phase relation. And here I would like finish my presentation, and basic equation of Josephson dynamics is presented. Maybe is useful for young people, and other parameters, symmetry and multiple character of new superconducting materials should be taken into account in calculation. For example, energy difference of in Josephson junction qubits, in phase qubits, and in flux qubits, and influence of this characteristic, this methods taken into account with calculation of effective critical current of Josephson junction in the case on harmonic current phase relation and in the case of frustration effects in multiband superconductors. Yes, thank you.
Okay, thank you for the talk. I appreciated having seen 5 slides from my lectures. Anyway, they're useful for community. Questions, please.
Thank you for a nice talk. So I have a question. So basically you are using the concept of washboard potential, but without fully, justified derivation from BCS theory. So do you see, actually I'm author of the paper about the derivation of washboard potential from BCS theory. So I would say, do you see any attempts to be more fundamental from the prescription, of Josephson effect? Because this is like reverse engineering. We have a washboard potential that is fulfilling the equations of motion, but actually, like BCS theory creates a more effective washboard potential that can be later approximated to the washboard potential that we are using. So can you make any comments on that?
Yeah, you are right. In principle, here is more a complicated form of current phase relation, but in general case, I show in the first slides, there are very simple equation, beta Mach-Camber parameter and second derivative of phase and this first derivative and sine sphere. We have 3 components and we use resistive shunted Josephson junction model because of
This is not a fundamental model.
yeah.
This is absolutely phenomenological.
Yeah, you are right. Yeah, for study of here, as you can see, here we generally in books, in calculations, in superconductor electrons, people using this equation. This one, if take unitless case of this parameter, this one is proportional to Mach-Camber parameter, and this one resistive term, and this one Josephson term. And mainly people use this variant because of, you are right, because of sometimes this relationship in tunnel junctions, yeah, you are right. In tunnel junctions, this sinus sphere seems more very simple and very, very simple. But in order to obtain results, we need in such analytical models and in such analytical equations because of there are, for example, in Bogoliov-Dejean equations, using Bogoliov-Dejean equations, we cannot get too simple sine sphere Josephson current. Here we have a more complicated expression. But in our studies, for example, in our calculations, it is enough.
Any further questions, please?
You have shown some expression for current where doubling of the phase difference occurs,
Yes.
or frequency doubling. I don't know. So where from does it come? What is the reason? No, frequency doubling, phase doubling, sine phi plus sine 2 phi.
Yes, this one.
Where from? What is the reason for such?
As I understand, for example, in the first paper by Sigrid Streiss, in the first calculation, taking into account D-wave character of or symmetry of order parameter in left-right superconductors, leads to this result, sine sphere. But here we have quotient 2 phi, theta le, and theta re, and inclusion this term related with taking into account D-wave character. And from another point of view, here, as you can see, experimental results. This equation. Here also we introduce sometimes maybe phenomenologically because of the but here there are experimental results which show that at low temperature, second term became more important and should be taken into account of study qubits on-site Josephson junctions. This Josephson junction on IPCO grain boundary Josephson junctions, and yes.
I would have a question where actually, what kind of materials do you consider? Because so far there have been no qubits made of high TC YBCO junctions. And the reason is that they are having very high loss. So the qubits require small dissipation. And once you take exotic materials like this, or two-band superconductors, then the losses are much larger than in tunnel junctions, conventional tunnel junctions, and the qubits don't work. So I wonder which particular materials, except for YBCO, did you consider here?
This one here generally is developed. Any model for the study, for example, is the case of, from the academical point of view, inclusion of second term, how will influence of to, for example, say energy distance between zero level and phase level, because of this one very important in the case of control parameters of qubits. And in the case of multiband superconductors, also we have introduced any similar terms, and there are another authors also takes such approach, and using such simple models, sometimes it is possible to get useful results. It seems sometimes for the experimentalists, but from the point, you are right, from the general point of view, in the case of qubits, there are special moments should be taken into account. Yeah.
Okay, thank you. Any further questions? Okay, let's thank the speaker again. And I'm honored to give you the certificate. Okay, thanks. Do we have the last speaker of the session? Okay. Okay, so the last speaker of the session, and last but not the least, is Jean-Daniel Bancal. And I suppose his slides will appear, and looking forward to hear his voice as well.
Yes, hello, can you hear me? So, yes, I'm trying to share my screen, but it tells me that there's another participant sharing, so I cannot share. Okay, let's try. Okay, now it should work. All right. Can you see my slide now? Can you hear me? Just checking. All right. Should I start?
Yes, yes,
Are you
please.
able to
Please
hear me?
start. Yeah. Yeah, we see
Okay,
you
okay.
and see your screen.
Thank you. Perfect, thank you. I was not sure about that. All right, so, well, let's start. And yes, thanks first of all to the organizers for putting up this conference and for giving me an opportunity to share some of our work with you today. And so yeah, this is a work on experimental quantum key distribution certified by Bell's theorem. And this is a work that we have, there's really a collaboration from several teams. So as you can see there, I think we are about 15 people on it. This includes a experimental team from Oxford, as well as theory people from Lausanne, Zurich, Geneva, and ourselves, Nicolas Sangouar and myself, from Paris. So, yeah, so what I would like to talk about today is probably a little bit different than most of the talks that you will hear at this conference. So I hope you enjoy it, nevertheless. And so you can also find the details here. And I should mention it's been published in Nature. And there are also 2 other works that are related that have those numbers there. So maybe to give some context, maybe you're just wondering, okay, what is quantum key distribution about? And so just very quickly, you at least heard of the recent Nobel Prize that was awarded to Alain Aspect, John Clauser, and Anton Zeilinger just a few weeks ago. And it was awarded for their experimental work with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. And so if you are curious to find out more about this, maybe you went to look at the scientific background put together by the Nobel Committee. And it mentions highlights of the development that has taken place over 40 years. Some of these experiments were done really 40 years ago. And that tells how this relates both to fundamental discoveries in quantum physics, as well as have direct relevance to practical applications. And the application that is mentioned in this document is actually quantum cryptography. So if you wonder how quantum cryptography is related to Bell inequalities, you are at the right place to learn more about it, because this is exactly the topic of our work. So without further ado, let's have a look at what a typical cryptographic task is about. And so here we have Alice and Bob, 2 parties that are distant. And a typical cryptographic task is to say that maybe Alice holds a string M, a string of bits, just a message. And maybe she has also additional information, maybe some K. And Bob only has K. And maybe what Ali wants to do is to actually send the M to Bob as well. So how could she do that? Knowing that they are at a distance from each other and they cannot meet. So she needs to send a message. And so one way to do that would be for her to actually take this string M and K and take the XOR of them and compute a new string S and send it over to Bob over a channel. And then if she does this, well, Bob will actually be able to recover the message M by taking the XOR of this message S with the string K that he has here. All right. So that would be one way to send a message, for Alice to send a message to Bob. And you might be wondering why do it this way rather than just send, for instance, M over to the channel. And the reason is that this very specific way to send a message has very good properties with regard to secrecy. And in particular, if we now consider that truly Alice is on her side, Bob is on his side, they both have maybe labs or homes that they know what's going on here, but outside is an environment that they don't control, and in which there could be an adversary here. And so the question is, well, if they use this encoding to send a message, the adversary only has access to the message S here, but doesn't have access to K. And so what information theory tells us is that having access only to S is not sufficient to gain any information on the message M when things are encoded this way. And so this particle scheme is known as the one-time pad, and it's actually the only encryption scheme that is proven to be secure. And so it requires another string K that we all just know as a key to encode the information. And so we see that secret or secure communication will basically amounts to having distant parties share a key K. And once they have this, then they are able to communicate securely. So this is what we'll be interested here, is the question of how to create a key between distant parties. And so this is what we call key distribution. And we could imagine, at first, we could just say, okay, let's try to create a key. And so we have Alice and Bob in their labs, and there's the channel in the middle, and maybe there's a protocol that they can follow, send some information back and forth, so that in the end they would have a key. Ka would be the result of this process for Alice, Kb would be the result of Bob's process. And ideally those keys, of course, should be identical, like here, and they should also be secret, which means that nobody in the middle should be able to have a copy, hold a copy of these. So if you just think about it a little bit, you should be able to convince yourself that such a protocol does not exist. It's not possible to create a key at a distance, because if such a protocol existed, then an adversary in the middle could play it with respect to Alice on one side and with respect to Bob on the other side, and hold a copy of the key that they obtained. And therefore, if such a protocol exists, it is not secure. So this is a typical attack of cryptography called the man-in-the-middle attack. And what this tells us is that we, in order to create a key, or for any secure communication to start with, there's a need for an initial secret, K0, that will be first shared by Alice and Bob in the start of everything. And in fact, you can show that this is sufficient then to authenticate communication. And so the real deal here is to know that,
recording stopped.
Starting from a key shared by Alice and Bob, how is it possible for them to expand this key, make it longer, in order to use it in various tasks? And so this problem was analyzed in computer science, and solutions were found, and this is what we use nowadays whenever we communicate online. And current solutions, they rely basically on computational assumptions. So since it's not possible to really do this without further assumptions, then they assume that, well, some operations are just too complicated to be done efficiently by an adversary. So even if he can listen to everything, we just assume that he's not able to perform those computations, and this provides some security. But the problem with that is that existing protocols rely on difficulty of problems such as the factoring problem, factoring a large number into factors, integer factors. And it is known today that well, since 1995 and the emergence of discovery of Shor's algorithm, it is known that that we have a quantum computer. This would be a task that is doable efficiently on a quantum computer. And so, of course, we don't have a full quantum computer yet, but well, efforts are being pursued in the world. And just to give you an idea of where things are at the moment, companies like IBM have worked on systems that are able to could make larger and larger, and currently they are about 400 qubits, noisy qubits, but still at their disposal. And current estimates are saying that, well, actually it would be possible to factor what is considered a difficult problem, a 2000-bit RSA key, with a quantum computer with between 10,000 and 20 million, which is very large still, number of qubits. And so we are not there yet, but somehow we are getting there. So we can really think about, okay, whether we want to find another another kind of protocols that would be resistant even in 10 years or 20 years to come. And well, if those classical protocols will break down, quantum theory actually provides also a solution to that. And this is what is known as quantum key distribution. And so how this works, or the idea behind that, is that if two parties, or two Alice and Bobs, share a maximally entangled 2-qubit state, well, this quantum state has very interesting properties. And in particular, a pure state is unentangled or uncorrelated to anything else. And at the same time, the outcomes of a measurement on a single state locally are fully random. It's not possible to predict what will be the outcome of, say, a sigma X or sigma Z measurement. So this is perfect. It's like unpredictable by an adversary. But at the same time, the person holding the other half of the singlet is able to obtain results that are fully correlated if that person performs the same measurement. And so this is exactly what we need for a private key, something fully correlated but unpredictable to any third party. And so based on this principle, quantum key distribution was developed over the years, and basically existing protocols relied on a number of assumptions, which is really small. We can just list them here. And so basically there are 5 assumptions. The assumptions are that quantum theory is correct. Then that the assumptions that, well, so Alice and Bob each have a lab, and of course no information should exit the lab, otherwise the security is lost. Then we need to be able here to choose between performing, say, a sigma X or a sigma Z measurement in a way that is independent, that cannot be controlled by an adversary. So we need truly random numbers, and then the post-processing, the classical post-processing must be done in a trusted way. And also the quantum devices, say the measurement operators that are realized here must be the one that we want. So in particular, that means that the devices must be well calibrated, trusted, and they must maintain perfect calibration. Basically, when we say we want to do a sigma X measurement, this should be really a sigma X, not something else. And under these assumptions, then it's actually possible to obtain really proven information theoretic security, meaning without any assumption on the computational power of an adversary. Meaning here an adversary could do whatever it wants as long as anything allowed by nature or by quantum theory. So that's all interesting, but the problem with that is that in practice, because these protocols have been realized over the past years, and you can even buy commercial devices. But the problem is that it's really, really hard to guarantee that a quantum measurement here is precisely what one wants to do. And in particular, any deviation opens a loophole, opens a way for an attack by the adversary and breaks the security potentially. So this was realized, and well, there are several solutions to that that are possible. And one way is to just find every time an issue is found, to find a countermeasure and a patch and go on, as is often done in security context, when there's nothing better that can be done, really. So that's one possibility. Another is to just go and try to really model the actual device fully from a theoretical point of view and try to find a security proof there. But this is just really impractical, because when you think about it, even just a photon detector, this is already a many-body system, and I think nobody here has the pretension to know fully how to describe an arbitrary many-body system. So it's kind of very tricky. And the third option that has been pursued and that we'll be interested here is to basically, on the contrary, try to lower the amount of modeling that is involved at the level of that theory to make sure that it can match what happens experimentally, sorry. And so what this means is essentially just look at all the devices as black boxes with some classical input and output, and just say, okay, we don't want to know what is really going on when we try to prove security. We just know that, well, when I press this button, then maybe the green light came down, and we say this is the low level of description that we want to put on our devices. And when we do that, we're already able to get rid of this fifth assumption, that is the problematic one. And this is what is called, referred to by device-independent
recording in progress.
Information processing in general. And so maybe that sounds like a fine idea, but how well, we'll have much less information about the system if we do something like this. So how can we still expect to find some level of security? And the key here is to basically play or test a Bell inequality, and this is what brings us back to Alain Aspect and others, because by playing a non-local game or Bell inequality, two parties are actually able to test in a black box scenario whether the system is close to a single state. And so this was formalized by Mayas and Yao and others. And so what this means is that by playing this game, the players are able to know that they have essentially a singlet, and as we know, if they have a singlet, there should be some level of security, because no third party can be correlated to them. So this was the basic intuition behind that, but it has been really formalized, and it's actually possible to evaluate and compute really what would be the uncertainty or the level of secrecy about the outcomes here as a function of this winning probability. So if we take this CHSH inequality or CHSH game, a score of 3/4, 75% is achievable classically, so it cannot have any secrecy. But quantum theory allows to go up to 85% of winning probability. And so we see that now it's possible to actually quantify as a function of the winning probability within this interval how much secrecy is there in the outcomes of the measurements inside the boxes. So, well, knowing this, we can try to now think about, okay, how could we leverage this to actually produce a key and to create a key between two parties. And so for this, we need to actually come up with a protocol, and there are two paths to a quantum key distribution protocol. One is quantum, is the generation of the data, and then there's a classical post-processing part that comes after that. I'll just briefly overview. So basically the data acquisition step involves an experiment of this type, where we would have, first, we need to create a state between Alice and Bob, an entangled state, herald it, and once the case, then Alice and Bob wants to basically isolate the system to make sure that nothing will come out at that moment. Once they are isolated, they can choose their measurement and perform the measurement and record the outcome. And there will be basically two types of measurement they can do. Either will have test rounds, which basically are moments where we want to test this non-local game, this Bell inequality, because this is what will tell us about security. And then sometimes we'll also have generation rounds, meaning we'll try to make sure that Alice and Bob have outcomes that are as correlated as possible, because this is interesting to have just more key. So basically, at the end of when repeating this at random over many rounds, then what the outcome of this will be that Alice and Bob will have each a string of settings, and of outcomes that are just strings of bits or threads. And this is the result of the quantum measurements. And once this is done, then there will be need for a classical processing. And the reason is because, well, the outcomes may contain indeed some unpredictability, but they are also not fully unpredictable. And also, their outcomes will have errors, so they will not always be identical to each other. And so to have a key, we need to just correct all of this. And so that's why the first step is actually to do error correction, meaning that Alice will reveal information about her results to Bob, to allow Bob to reconstruct a copy of Alice's outcomes. And this should be done by revealing as little information as possible, because all of this information will be available to the adversary. And after that, they'll need to check whether indeed the Bell inequality is violated strongly enough. Because if an adversary is there, then the violation will disappear. So that's the way of checking that no adversary is on the line. And then there will be privacy amplification, meaning concentration of the secrecy in the key, and at the end they need to still authenticate their communication, as we have seen, because without authentication there's no security. So with this, okay, let me just pass over the error correction and just mention maybe something about the security analysis. How can we analyze the security of such a protocol? And so there are different levels of security that one could be interested in. So in this context where an adversary has access to the channel, and basically we could imagine that at every round the adversary could be here and perform a measurement on what is going on. And if he does that, always the same measurement, we call that an individual attack. Or he could also do another measurement, but just an interaction each time. That would be a collective attack. But what we are really interested in is to basically obtain a key without enforcing any constraint on the adversary. That's the only case in which we can obtain information theoretic security. And so this would be in the case of coherent attacks, which is what we'll be interested in and in this work. And so the secrecy then can be formalized. We can really quantify how secret the key is, and in the end it will boil down to computing a smooth mean entropy. Maybe I'll just go over that so we can have a look at the setup and of the actual experiment. And so what does the setup look like? And this is the setup from the Oxford group. And so they have two strontium atoms that they hold in distinct traps, ion traps. And what they can do is they can entangle or they can let their ion emit a photon and stay entangled with the state of the atom. They can do that on both sides and capture the photon in the fiber. And what they use is then they use a Bell state measurement here in the middle to perform basically entanglement swapping. And when this is successful, then it announces, it heralds the entanglement between the two strontium atoms. And when this happens, then the protocol goes on, and basically they isolate the ion from the fiber by moving it away from the focus of the lens, and then they perform a measurement of the state of the strontium atom, and they do that on both sides. And by doing this, they're able to test Bell inequality between them. And so the CHSH score they observe is about 2.68, which is really remarkable for this kind of setup. And the error in the same, when using the same basis on both sides, is about 1.5%, which is also extremely low. And so by looking at the security analysis with these parameters, we were able to show that, well, there would be no key for any number of measurements that is less than 1 million. We would not be able to prove that. But starting from 1 million round, we would have actually the possibility to get a key with very good security. So security parameter of 10 to the minus 10. And so basically we went for a number of round which was 1.5 million. And here's the result. So the data acquisition was 1.5 million rounds. And given the Bell inequality violation observed on those rounds, we're able to certify that there would be at least 400,000 secret bits. So bits that are really unpredictable by the adversary. Now, out of those, we still had to sacrifice 3/4 to allow Bob to correct all his own errors. And that left us with about a little bit short of 100,000 bits that were generated during the experiment. And this is still much larger than the 256 bits that were used and consumed by the protocol, and therefore demonstrating an expansion of the key. So here is, you have a picture of the key. Here, the key of Alice and the key of Bob. And we actually used it to encrypt an image of John Bell. And you can see here how a one-time protocol works. So the key is encoded, encodes this image. This is the message that is sent over a public channel, and that's what an adversary can see. But then Bob, with a copy of the key, is able to recover the initial picture. And so that was the actual data of the key. So with this, yeah, I just want to share that we were able to expand the secret key with information theoretic security and assuming only classical control over the devices, or device independently if you want. And so what's next would be to go to larger distances. Here the distance was about 2 meters between Alice and Bob, and to maybe also have quantum memories to avoid reopening the labs every time a new system needs to be distributed. And there are also a number of theoretical ways to improve things. And I'll just mention also that we are looking for enthusiastic and talented postdocs. So if anyone is interested to come and join us in Paris, he's happy to we'll be happy to hear about him. And with this, I thank you all for your attention.
Thank you for the talk. Indeed, it's somewhat outside the field, so I'm wondering if there are questions. Hope there will be. Yes?
Thank you for a very nice talk. So I have a question. So how far is this technology which you have presented from commercialization, I would say. So what would be the practical cost of usage of this quantum network?
Yeah, thank you. That's a very good question. So there is a lot of effort being done throughout the world, and including in, especially in Europe, to basically build quantum networks over large distances. And what I presented is really just the very first time that we are able to produce a key, and that's on a very short distance, just a few meters. So obviously there's still a lot of work that needs to be done, especially experimentally, but also theoretically, to improve things and make things easier. And especially maybe we want to go towards photonic systems, maybe, because those are go well over fibers, so over longer distances. And there are efforts also in this direction. So I would say at the moment, at least this particular technology is more still at the level of first demonstrations, and will still take time, I think, to really come up with something that can be sold as a device. But that could be just a few years down the road, I would say, for the IQKD. But for really, say, the idea of having quantum networks, that would be the equivalent of what we have today as internet, but in a quantum version. That probably will take more. I mean, there's much more work to do. Currently, the longest distances that are demonstrated are of the order of 1 kilometer, something like that. So that gives you, I guess, an idea of where things stand.
Great, thank you. Any further questions? Okay, again, thanks for this talk and also broad introduction. I think we got something what you about to convey. Let's thank the speaker once again.
Awesome. Thank you.
This concludes the session, and thanks for the audience being present in the end.